In this question, we're asked to find the area of the region cut from the third quadrant by the cardioid 1 plus cosine theta. R equals 1 plus cosine theta. So we need to know what that looks like. And we go to your cheat sheet and you look at the graph of cardioids, and you see that when there's a cosine involved, that the graph looks like that. Third quadrant means that we're focusing on that purple part there, and we need to find the area of the purple part in the third quadrant. And when we find area in polar, it is a double integral with the 1 r dr d theta. We need to find the r bounds. We need to find the theta bounds. The way we find the r bounds is we go radially outward from the origin through the region. And so your r bounds are going to be 0 for the origin and 1 plus cosine theta for the upper bound. And then this gets swung in the direction of increasing theta. We have to figure out what the theta are. When theta is equal to 0, double check and make sure that r is equal to 2. R is 1 plus the cosine of theta, and so we'll have 1 plus the cosine of 0. Yep, r is equal to 2. When theta is pi over 2, make sure that r is equal to 1. So things are happening like your eye is seeing them. It's not, you're not being deceived. 1 plus the cosine of pi over 2, which is 0, means, yeah, you're at 1. So quadrant 1 is done between 0 and pi over 2, like you would think. Check on pi to make sure that you get a 0 for that. Cosine of pi is -1. So, yep, they zero out. And so then your thetas go from pi to 3 pi over 2. Double check it. When theta is 3 pi over 2, cosine's back to being 0, so you're at 1. Outward would be -1 on the y-axis. So that works out. Pi to 3 pi over 2. R dr d theta. That will be the area of the purple region there. Okay. Leave the outside integral alone. And integrate r. Get 1/2 of r squared. And you have to plug in the bounds of 1 plus cosine theta and 0. And then later we integrate with respect to theta. When you square out 1 plus cosine theta, you end up with, let's pull the half all the way out, and we'll have 1/2, the integral from pi to 3 pi over 2. We get a 1, we get 2 of those cosine thetas, and then we get cosine squared on theta. Now for cosine squared on theta, we go with the half angle identity, or double angle identity. I think it's actually half angle, the official name of it. And so we replace cosine squared on theta with 1/2, 1 plus the cosine on twice theta, distributing. That gives us 1, the double cosine theta, and then a half and half the cosine on twice theta. So put that together, and we'll call that 1 combined with the half. We'll call that 3/2. We're going from pi to 3 pi over 2. We have this 3/2 that we have to integrate. We have 2 cosine of theta that we have to integrate. And we have half cosine of twice theta that we have to integrate. Don't forget the half that's on the outside. So we end up with 3/2 of theta double the sine of theta. And the 1/2 and the extra 1/2 that comes in here will double up to give you a fourth, or square up to give you a fourth, the sine of twice theta. But when you put these guys in there, we're going to find out what happens. The 1/2 stays on the outside. We get 3/2 of 3 pi over 2. And then we get double the sine of 3 pi over 2, which is a -1. And then we get a fourth of the sine of 3 pi, which is 0. Then we plug in pi, and we get 3/2 of pi, but the sine of pi is 0, and the sine of double pi is 0. And so those guys zero out. We end up with an answer that is 9 pi over 4, take away 2. And then we take away from that 3 pi over 2. Let's work that out. So is that 3 pi over 4? 9 pi over 4 minus 3 pi over 2. 9 pi over 4 minus 3 pi over 2. Double 3 pi over 4. I think that is, yeah. Okay, great. So we have the half that's on the outside. We have 3 pi over 4 minus 2. And so we can distribute if you want, or leave it alone. Doesn't matter. If we distribute, our answer to the question is 3 pi over 8 minus 1. That's the area in the third quadrant of a cardioid that's called 1 plus cosine theta. Okay, so this is the solution. Comment down below if you have any questions. But, yeah, there it is.